Yes, hello everyone. Today we are going to discuss regarding inductance of composite conductor lines. So we are going to find the expression for inductance of composite conductors, and we are going to take the reference as a single phase two-wire system for our analysis. So you might be wondering, why can't we do it for a three-phase system? Yes, we can also do it for a three-phase system, but considering the analysis, I'll restrict the analysis only to single phase system which is being there, and for a two-wire system. That is, generally once you have a single phase system, you'll be having a two-wire system also being present there. So now if you consider a two-wire system, so conductor P and conductor Q are the two conductors, composite conductors, which are said to be there in the system, and each and every conductor like conductor P are having several such strands, so A, B, C, and so on up to X. So as many number of strands that is being designed, we are having such number of strands. Equal number of strands are being present there in conductor Q also, because it is a single phase two-wire system. So A to A dash, B to B dash, C to C dash, and the number of strands that is there in conductor P is said to be there in conductor Q also. So we can generally say that as many number of strands that are being present there in conductor P, so there will be equal number of strands that are being present there in conductor Q. So these are the two conductors that are being present there in a composite conductor, considering a single phase two wire system. Moving on to the next one, I need to find out the current that has been there in such a system. So for conductor P, my analysis for conductor P is consisting of X identical parallel filaments. So if you have done the derivation, so I have X number of identical filaments that is being there for conductor P, and each filament carries a current of I by X, and conductor Q, which is carrying Y number of parallel identical filaments. So each filament is having a current of I, that is with a negative direction, minus I by Y. So Y is generally the number of parallel filaments that are being present there. So you have the conductor which Y, which carries a current of I amps in the opposite direction. That's the reason why you have a negative direction that is being present there. So to the conductor X, as it is forming a return path. So if you have done the derivation of single phase two wire system, so I1 plus I2, that would be equal to 0. Here I have Ix and Iy that is being present there. So that's the reason why you call this to be in a negative direction. So I want the flux linkages that is being present there, the flux linkages that are being present there for the filament A in conductor P due to all the currents in the filaments. So what is the expression that has been there? So phi A, I have it as 2 into 10 power minus 7, it is common. I by X, that is the current. So ln of 1 divided by dAA. So considering A conductor that is there in A filament that is present there in conductor P, I have this expression being written, and the current flowing through that conductor is I by X. So that is the expression whatever I have written here. Similarly, A to B, yeah, this one, this is the distance that is being present. Next, A to C, this is the distance. So similarly, I can write it for the all the parallel filaments that are being there in conductor P. Next, conductor Q. For conductor Q, I have from A dash, A, B dash, A, C dash. Similarly, you can write it. And the current is said to be in an opposite direction through that of I by X. I can write it to be minus I by Y in all the cases till the Y number of filaments that are being present there. So next one, I can do it to be, yeah, I can extend the analysis. I can take I by X and I by Y as a common factor, and I can make the certain simplifications that has been listed out here. So this is the minus sign and the plus sign, I by X and minus I by Y in both the expressions that are being present there, and I can write this one to be in terms of the logarithmic analysis. So how do I write it in terms of the logarithmic analysis? 1 by y ln can be written as root y, that is there in the numerator part. So this one is being present there in the numerator part, and this one is being present there in the denominator part. So I is taken as a common factor in I by x and I by y, and you have this expression. If you recall the simple logarithmic rules, you will be able to understand it. So how did I write root y, that is under d a dash ab dash and till ay, and similarly till daa, dab and dax. So now I want the inductance to be analyzed, that is for the parallel filament A. So how do I write it? So I know the flux linkage and the current relation that is being present there for filament A. So for filament A in conductor P alone, LA is given as phi A divided by I by X. So it is not I alone, it is I by X. So how do I write it? 2x into 10 power minus 7. This X, whatever that's been present, it is the same X that is being present here in the denominator. So again, X term is being present, and I can write this equation here. So next one, the inductance of filament B. How do I calculate it? So if you can recall, so wherever you have the A, okay, so if you see this, so this is where, yeah, so I've taken this as a reference as the first subscript. So you have subscript being written as A dash. The first letter that you can replace will be the inductance of filament B, and subsequently if you write it for the next one, it will be for the filament C there. So if you can underline, yeah, this one, if you can see, the same thing holds good for the other equations also, the other filaments also, which has been there, where LB is given as phi B divided by I by X. Again, 2x into 10 power minus 7 ln of the y root and the x root that is being present there. So next one, I have the average inductance of filaments. The average inductance of the filaments of conductor P. It has been given as L average, that has been written as LA plus LB plus LC plus up to LX. So that is the number of strands that are being present there, and the inductance of all the strands are being present to calculate the average inductance of filaments of conductor P. So divided by X. So this is how we calculate the average. So simple average we'll be calculating it, and the conductor P consists of X number of parallel filaments. If all the filaments are of equal inductance, then inductance would be 1 by X times the inductance of the one filament that is being present. So if L average is to be like LA, LB, LC, and all the things are to be equal, you can take the sum of it and divide it by the number of filaments that is being present there. So all the filaments have different inductance, but the inductance of them in parallel is 1 by X times the value of the inductance that is being present there. So that is nothing but the parallel average inductance that you calculate. So you can calculate it by the parallel combination 1 by X times, if it is in there in parallel combination, 1 by X times the average inductance value that is being present there. So next one, if I want to calculate the inductance of conductor P. So I know L average. So how do I calculate LP? That is inductance of the conductor P alone. I can write it as L average divided by X. So L average, I can write it by this. Divide by X, it is already being there. I can write it as 1 by X term again, which is being present. So substituting the values of LA, LB and L6 in the equation, we can write, and we can have this equation for LP. So this equation, what you get here, so this is the equation for LP that is being there, which is common for the inductance of conductor P. So 2 into 10 power minus 7 ln of root xy d a dash a b dash a y b a b b dash and so on. So if you can extend it, if you can see the subscript being present there carefully, a dash. Next one, if you can write this one as b a dash, and similarly you can write it here b a dash. So this one is a dash here. If you can write it a dash, a b dash, and you can write it as x squared a b and ax. So if you can recall the expression whatever that is there, you can write it easily. This expression, you can make use of this simple concept called as cyclic symmetry, and you can write it. So now if you carefully observe the above expression, so this logarithmic term which is there, so has a fraction term being present. So this is the numerator part. I'll write it as nr, and this one is the denominator part of the logarithmic expression that is there. So the numerator of the expression in the logarithmic term is the xy root of xy terms that is being present there. For example, if I have two strands and two strands, that is fourth root of four terms which are being present there in the equation. So these terms are nothing but the product of distances from all the x filaments of conductor P to all the filaments of conductor Q. Yes, so if you can write it, yeah. So these terms are nothing but all the filaments of conductor P to all the filaments of conductor Q. XY root of the product of XY distances is called as geometric mean distance. So GMD, geometric mean distance, it is being termed as DM. So it is called as mutual GMD between the conductors which are being present there. So that is between the conductor P and Q. So it is being termed as DM. So xy root of product of xy distances is called as geometric mean distance between conductor P and Q. So next one, this is what I wanted to say, which is important. So geometric mean distance, and it is also called as mutual GMD. So this is important term when it comes to composite conductors. So xy root of the product of xy distances in a composite conductor containing where x is the number of filaments and y is the number of filaments in both the conductors that are being present there. So there you can call this one to be geometric mean distance. So that is called as DM or GMD, geometric mean distance between the conductors. Next one, the denominator of the above expression, that is that was there in the logarithms, so had x squared as the term which is being there, x squared root of x squared terms that are being present there, x squared root of x squared terms. There are x filaments, and for each filament there are x terms which are consisting of r dash, such as daa, dbb and dcc. That's what. So without the a dash term or the b dash term that is being present there, you can write it with x squared root of x squared terms which are being present there for that filaments times the distance for that filament to every other filament in the conductor. It is just like having the GMR, which is nothing but the geometric mean radius for each and every filament that is being present there. So GMR, it is being present, yeah. So you can call this to be self GMD. GMR can also be called as self GMD, where you will be having the representation notation given as R dash. So R A dash, R B dash. This is R dash, which is for a separate filament like A, B, C, D, or many number of filaments that are being present there for each and every conductor that is being present. So LP is 2 into 10 power minus 7 ln of dm by ds. So this is the final expression that is there, that is Henry per meter. So 2 into 10 power minus 7 ln of dm by ds. So this composite conductors has having many parallel strands that are being present. The inductance of composite conductor Q can also be obtained in such fashion. So the same expression that are being present there for conductor P is also valid for conductor Q. So LP equals LQ is 2 into 10 power minus 7 ln of dm by ds. So I want to calculate the inductance of the line that is being present there. So inductance of the line, I can overall calculate it as L equals LP plus LQ. So that is being present there, and you can make down the expression, or you can remember this expression. If you add it, you'll be getting like this: 4 into 10 power minus 7 ln of dm by ds Henry per meter. So L equals 4 into 10 power minus 4 ln of dm by ds. If I want to express in kilometer, that would be Henry per kilometer that is being present there. So moving on to the next problem. So you can solve a problem based on that. If you can read it. In a single phase line as shown below, conductors A and A dash are in parallel to form one conductor, and conductors B and B dash are in parallel, which forms the return path. Calculate the total inductance of the line per kilometer, assuming that the current is equally shared between the two parallel conductors and the conductor diameter is 2 centimeter. So 2 centimeter is the conductor diameter, and these are the conductors that are being present there. So let me move on to the solution now. And just before I move to the solution, I have this parallel conductor, say conductor A and A dash, B and B dash that is being present, and between these two I have 100 centimeter as the distance there. So A dash, the distance between both of them is 20 centimeter, B and B dash is 20 centimeter, and A dash to B, you have the distance to be 100 centimeter. So this 100 centimeter is generally called as, yeah, so A to A dash, the distance between the conductor or filament is said to be 20 centimeter, diameter is said to be 2 centimeter. So this one is generally called as the conductor to conductor distance. Generally we call that to be from A dash to B, so which is being present there. So that is the representation of the figure. So next one, if I want to analyze the solution to the given problem, so distance between the conductor, as you can see, it is A to A dash is 20 centimeter. So that is from the center to center that is being present there. So this one is said to be 20 centimeter. Okay, next I have the diameter of each conductor 2 centimeter, and from diameter you can get radius as 1 centimeter, and r dash you can write this to be 0.7788 into 1, that is 7.788 into 10 power minus 3. So how many number of strands are being there in each conductor? Two strands, that is in parallel in each conductor, that is being present there. So loop inductance is calculated as 4 into 10 power minus 7 ln of dm by ds that is being present there. So dm is the mutual GMD that is being present. And next one, if I want to calculate the mutual GMD, I can calculate it as fourth root. So this is x into y, that is dm. So DAB, okay, I told you for A, I have B and B dash that is being present there, and for A dash again I have B and B dash. So DAB, DAB dash. Next D A dash B, A dash, yeah, A dash B and A dash B dash that is being present there. So let me write it as A and A dash. So this one is to be A and B, A and B. Yeah. Okay, so this is how I can write D A B. Yeah, this is B and this is B dash, and again this is A dash, this is B, and this is B dash. So A B dash, A dash B, and A dash B dash. So if you can measure the distances, it would be A B is 120, A B dash 140, A dash B is 100, A dash B dash is 120. So this you can write it, and you can get dm as 1.1915 meter. So you can write it like that. Next one, if you want to calculate ds, it would be like this: fourth root x squared. So that is x squared that is being present there. So that is 2 squared. You can write it as 4. So you can write it as DAA, DAA dash, DA dash A, and DA dash A dash. So that is A, that is within the conductor, within the one single conductor, you can calculate the self GMD or geometric mean radius. So this is ds, which is 0.0394 that is being present. The loop inductance being present there as 4 into 10 power minus 4 ln of 1.1915 divided by 0.0394. Loop inductance has been given as 1.3636 millihenry per kilometer. So that's how you can calculate the loop inductance. 4 into 10 power minus 7 ln of 1.195 divided by 0.0394, that is the loop inductance, as 1.3636 millihenry. So loop inductance is both the conductors, the current going path and the return path that is being present there. So both the inductance has to be calculated and it has to be substituted. So you'll be getting loop inductance as 1.3636 millihenry per kilometer. Moving on to the next derivation, I have inductance of a three-phase system. So we are moving now to three-phase line or a three-phase system line with equilateral and symmetrical spacing. So when I say equilateral and symmetrical spacing, I have three conductors. Once I have three phase, I'll be having three such conductors that are being present there at equal distances from each other. So when I say it is at equal distances from each other, the distance will be d for each and every conductor that is being present. So I'll be placing the conductors in such a way that the conductors A, B, and C in a three-phase line. So three conductors are equally spaced at the corners of a equilateral triangle having the radius r. So if I have the radius r being present there, so I need to write the flux linkage with respect to the first conductor. Let me take the first conductor as A, and I can write the flux linkages of conductor A. So here you are said to be a balanced system for our analysis. 2 into 10 power minus 7 IA into ln of 1 divided by r dash. So this one is 1 divided by r dash. Next A to B. So IB, that is the current. Next ln of 1 divided by D. Next IC, ln of 1 divided by D. So here we are doing it for a three-phase balanced system considering the distances to be equal. So DAC is said to be D and DAB is said to be D again. So for a balanced system, IA plus IB plus IC, IA equals minus IB plus IC and IB plus IC is minus IA. So that is being present there. So next one, if I want to calculate it, so the equation 1 becomes 2 into 10 power minus 7 IA ln of 1 divided by r dash and IA ln of 1 divided by D. So if you can rewrite the equation using simple logarithmics, phi a is said to be 2 into 10 power minus 7 into IA ln of D divided by r dash. Phi a by IA, that is LA, that is being present there, that is 2 into 10 power minus 7 ln of D divided by r dash. So that is being present there. So the same expression is valid for both the remaining phases, that is LB and LC. You can calculate it as LB and LC because of the symmetry of the conductors B and C, which will have the same inductance as that of conductor A. 2 into 10 power minus 7 ln of D divided by r dash. So next, for a standard conductor, I can write this one to be ds. So r dash, I can write this to be ds. D divided by ds can also be written, and that's the final expression for the three-phase line considering a symmetrical with equilateral spacing of the conductors, that is the three-phase conductors that is being present there. So this is one thing that you can remember, and you can rewrite the equations that are being present there. So in the next one, we can generally make use of the numerical problem. So you can generally substitute it. The three-phase system can only have such equations that are being present there. So in the next one, we'll go for the unsymmetrical, and the distances are said to be varying in nature. Okay, thank you.